We have talked about the directional derivative in the gradient video, the divergence and the curl in 2 other videos. Now, it's time to try an exercise to find out if you can determine when these are 0 without doing calculations. So I recommend that you watch parts 2.2, 2.3 and 2.4 before watching this video. The first case will be a circular pipe. This one has the same flow velocity as our rotating flow case in the beginning of the video about curl. The second case will be a pipe with equal width where the flow accelerates. The third case will be a pipe becoming more narrow while the flow velocity increases. The final case will be a flow with a vertical velocity gradient. In the first exercise, we are going to check if the directional derivative is 0, here represented by our convective acceleration term from the gradient video. The trick here is to think about what happens when a particle travels through the flow. If the particle changes its velocity, this term will get a value. If the velocity is constant, this is 0. Pause the video and think which of these cases that will have this convective acceleration term 0. To analyze this case, start by drawing streamlines and let particles travel along these lines. Do they change their velocity? In our first case, the particles turn. Hence, they experience acceleration and the term is non-zero. For the second case, the streamlines are straight. We can however see that the particles are speeding up. Hence, they are accelerating and the term is non-zero. In the third case, the situation is similar to the previous case. The streamlines are straight, but the particles will accelerate. Hence, the term is non-zero. Finally, for the last case, the particles will have different velocities, but each one of them will keep a constant velocity. This means no particles accelerate, and this term is 0. Hence, this is the only case that don't have any acceleration. Next up, the question is, which cases are divergence free? The test we use to determine if a flow has divergence or not is to consider what happens to the density of the particles in the flow. If the particle density stays the same, the flow is divergence free. A positive divergence decreases the density and a negative divergence increases the density. Now, pause and think about which cases that are divergence free. For the bend, the particles are mainly traveling around in a circle, and this at a constant speed. This will cause the density to remain the same, hence no divergence. For the accelerating flow, we clearly see a decrease in particle density as the particles travel. We can therefore conclude that we have a positive divergence. For the case when the pipe gets more narrow, the decrease in width compensates for the increase in velocity. Hence, we can see that particle density stays the same, therefore the flow is divergence free. Finally, for the vertical velocity gradient, we cannot see any change in the particle density either. Hence, we can conclude that this case is divergence free. The only case that has divergence is the accelerating flow with constant width. In the final example, we are going to check which cases that are irrotational, meaning that the curl is 0. The test here is that we should place a cross that can move freely with the flow. If this cross starts to rotate, we have curl. Please pause the video and think about these 4 cases. The first case with the bend is a bit tricky to see, but it is the irrotational outer flow from the curl case. Hence, this case does not have any curl. The accelerating flow will push equally on the cross, and we can expect it to travel with a flow without rotating. Hence, the flow is irrotational. The situation for the next pipe is about the same. There's nothing that can cause the cross to start rotating. Hence, we conclude that the flow is irrotational. Finally, with the vertical velocity gradient, we have a higher flow velocity on the upper part of the cross. Hence, this part moves faster and the cross will rotate. Therefore, we have a curl for this case. This is the only case here that experienced curl. This will also mark the end of this exercise. Thank you.